Welcome. In the last lecture, we saw the numerical solution to the phase field equation, to the Kohn-Hilliard equation, and we also tried to calculate the interfacial energy associated with the interface in the Kohn-Hilliard model. We found that there are two terms that contribute to the interfacial energy, and they contribute equally to the interfacial energy. In this lecture, I want to show analytically some of these results, and they are all possible only in one dimension. In more than one dimension, it is difficult to get these analytical solutions. I am not even sure if they are available, but in any case, so we will compare the 1D solution with the analytical solution, and then when we go to 2D onwards, we will do everything numerically, and in this course we will do only up to 2D. 3 dimensions require lots of computational power, and Octave is not the best way to code in 3 dimensions. Then you have to use a programming language like C or Fortran and write your codes in that language so that calculations can be carried out. So let us start with the free energy functional with which we started. The free energy functional is this is the free energy function. Now, I am going to write this for the one dimensional case. So, f is equal to integral f0 of c this is the 1D case where f0 of c is a function that we assumed a c squared into 1 minus c whole square. Of course, the analytical solution that we are going to derive is more general. It can also be derived for a case where we do not assume for any form for f0 of c except for some boundary conditions, but we will first derive the analytical solution for this specific case, and we will come back to the more general case later after we do this derivation. Now, what we had is a free energy functional like that. This is our f0 of c, right, as a function of composition, and it had a maxima at 0.5, minima at 0 and 1. And so what we have, so in the more general case, when you have free energy as a function of composition given like that, and when you draw a common tangent, from the classical thermodynamics we know that for any composition that you take, the free energy is written. Suppose you take some composition C, then the free energy for the mechanical mixture is nothing but mu b times composition plus 1 minus c times mu a, where c is the composition of b. Okay. So, this is the mechanical mixture free energy where interfacial energy is not accounted for. Okay. Now, in our case it so happens that c is 0 and c is 1. So, at both the cases, if you take c and so this is the equilibrium c that we take, 1 minus so c for the, let us call them as alpha and beta phases. So, c beta equilibrium and c alpha equilibrium. Okay. So, those are the two end compositions for which the free energy is written. Now, in our case, because this happens to be 1 and this happens to be 0, this entire quantity is 0. In other words, like I explained in the last class, this is f by nv. Okay. This is f by nv per atom. Okay. So, because this is per atom. So, we can see that the interfacial energy per atom, that is sigma, is nothing but f by nv, because you take this quantity and you subtract this quantity, then you get the interfacial energy, because that is the excess free energy associated with the interface. and this term is already 0. So, our reference with respect to the mechanical mixture is put at 0. So, this itself is the interfacial free energy. So, we have F 0 of C plus kappa dC by dx whole square dx. So, I am assuming that I have a case where the composition becomes C equal to 0 and so as x goes, so let us take 0 here, and so this is x equal to 0. So, as x goes to minus infinity it goes to 0, as x goes to plus infinity it goes to 1. So, there is an interface in the middle. So, this is the case that we are considering, and we are trying to calculate this interfacial energy, and according to the thermodynamic definition of interfacial energy, which is the excess free energy associated with the interface, we see that in our case this quantity itself is the interfacial energy. Now, we want to minimize this interfacial free energy. The system would prefer to choose that interface profile which minimizes the interfacial energy, because this is the excess free energy. So, it would like to make it as small as possible. So, the problem of identifying the interfacial free energy becomes a problem of minimizing this functional, because it is the same functional as our Cahn-Hilliard free energy functional. We know how to write the Euler Lagrange equation. But before we do that, I want to go back to the variational derivation that we did for the Euler Lagrange equation. I want to take the Euler Lagrange equation. I want to slightly modify it so that it becomes easier for us to get the analytical solution in this case. So, the Euler Lagrange equation we had is dou f by dou y minus d by dx of dou f by dou y prime equal to 0 if f is a function of x, y and y prime is nothing but dy by dx, right. Now, in the current case we have in the place of y c and in the place of y prime dy by dc by dx, and x is the variable, position variable, x comma c comma dc by dx. So, this is the variable that we have for this function. So, in that case it becomes dou f by dou c minus d by dx of dou f by dou c prime is equal to 0. So, this is the Euler Lagrange equation, but this form of Euler Lagrange equation can be simplified a bit if we look at a case where f is not an explicit function of x, which is the scenario in our case, because remember the f was nothing but, so I should use a different symbol. This is okay. So, let me go back and let me change the symbol a little bit. Let me call this as script f, and what I call as f is basically this quantity. Okay. So, the integrand is basically the f that I have. So, that is Euler Lagrange is written in terms of the integrand. So, when you had I is equal to integral f dx, then that is the Euler Lagrange equation. So, in our case we call this as capital F or script f, and this is f dx. So, this is what we are writing. In our case f happens to be f 0 of c plus k dc by dx whole squared. So, obviously f is not an explicit function of x. In that case this equation can be simplified a little bit. So, let us do that simplification part first. So, let me take this expression. So, this is a general result from calculus of variations which we are going to use. So, let me take dou f by dou y minus d by dx of dou f by dou y prime equal to 0. Let me multiply by y prime dou f by dou y minus y prime d by dx of dou f by dou y prime equal to 0. Okay. Now, dou f by dou y prime, so let me let me do this. So, when we have dou f by dou y minus d by dx of dou f by dou y prime equal to 0, this implies that dou f by dou y is equal to d by dx of dou f by dou y prime. Okay. Now, we multiplied this by y prime. So, we had y prime dou f by dou y minus y prime d by dx of dou f by dou y prime equal to 0. Let me consider d by dx of y prime dou f by dou y prime. That will be equal to, so y prime d by dx of dou f by dou y prime, that is what we have here, that is the term, plus there will be an extra term. So, that is y double prime dou f by dou y prime. Okay. So, now d by dx of y prime dou f by dou y prime, that is equal to this term, but we know that that term is nothing but y prime df by dy, because this is equal to 0. So, we get y prime dou f by dou y plus y double prime dou f by dou y prime. Now, the total differential of f df by dx is nothing but dou f by dou x plus y prime dou f by dou y plus y double prime dou f by dou y prime. So, this is from calculus, this is an identity, d by dx is dou by dou x plus y prime dou by dou y plus y double prime dou y prime, if f was a function of x, y and y prime. So, this is an identity. Now, if f is not an explicit function of x, this term is not there. So, the right hand side can be basically written as df by dx itself. Okay. So, if we do that, we get this result, namely that d by dx of y prime dou f by dou y prime is equal to df by dx. So, this is valid only if f is not an explicit function of x. Okay. Calculus of variation textbooks basically deal with several cases where f is not an explicit function of y prime, where f is not an explicit function of y, and so on and so forth. So, this is when f is not an explicit function of x. So, Shames and Dim, for example, this is case 3, I think, in their cases that they discuss after deriving the Euler Lagrange equation. So, in any case, so this can now be written as d by dx of y prime dou f by dou y prime minus f is equal to 0. That means, y prime dou f by dou y prime minus f is equal to some constant, let me call that as alpha, where alpha is some constant. Now, this constant alpha should be 0, because remember the scenario that we are looking at. So, I have this quantity, the composition profile, which is like this. So, at the extremes where both the, because f consists of f0 and dc by dx, both are 0, because this goes to 1, this goes to 0. So, there are no gradients. So, dc by dx term is 0 and c is 0, that means ac squared 1 minus c whole squared is 0. So, this quantity. So, this quantity becomes 0, and because dc by dx is 0, this quantity is 0. So, alpha is 0, we know at these 2 points, because alpha is a constant, then if it is 0 at any point, we know that that constant is 0. So, we have this result, namely y prime dou f by dou y prime minus f is equal to 0. Remember, in our case y prime is dc by dx. So we have this dC by dx dou f by dou dC by dx minus f is equal to 0. We have assumed f to be a c squared 1 minus c whole squared plus k dC by dx whole squared. So, dou f by dou dC by dx, this is not dC by dx. So, it becomes 2 kappa dC by dx. Now, if you take so dC by dx and multiplied by this, so that is nothing but 2 kappa dC by dx whole squared minus f is this a c squared 1 minus c whole squared minus k dC by dx whole squared equal to 0. So, 2 kappa dC by dx whole squared minus kappa dC by dx whole squared is nothing but kappa dC by dx whole squared minus a c squared into 1 minus c whole squared equal to 0. So we get this expression. So, this is nothing but the Euler Lagrange equation in our case, which can further be simplified. So, let us take that expression and try to, so that becomes an ordinary differential equation that you can see. So, we will try to solve that. So, let us take that expression. So, kappa dC by dx whole squared minus a c squared into 1 minus c whole squared equal to 0. That means, dC by dx whole squared is equal to a by kappa c squared into 1 minus c whole squared. Let me take square root and call this quantity beta is equal to square root of a by kappa. So, what happens? dC by dx is equal to beta times c into 1 minus c, right. So, this is the ordinary differential equation that we want to solve, and to solve that, so let us do that. dC by c into 1 minus c is equal to beta dx. To solve this, we have to split it into partial fractions. Okay. What is partial fraction? I want to write 1 by c into 1 minus c as equal to some a by c plus some b by 1 minus c, right. So, what is the a and b values? So, that it becomes a dC by c and dC by 1 minus c. So, I can integrate it because that is just logarithm. So, what is the a and b which will give me that? So, let us do that. So, I have a by c plus b by 1 minus c is equal to 1 by c into 1 minus c. So, let us multiply a minus ac plus bc by c into 1 minus c is equal to 1 by c into 1 minus c. So, that means a is equal to 1 and b minus a is equal to 0. That implies b is equal to 1. Okay. So, you can see, so we see dC by c plus dC by 1 minus c, because so what this means is 1 by c plus 1 by 1 minus c is equal to c into 1 minus c. This is 1 minus c and that is c. So, that is 1 by c into 1 minus c. So, that is what we basically have found out. Okay. So, in general case, I mean if you do not know this also, it does not matter, you can write a and b and find the partial fraction. So, which is precisely what we did. So, because it is dC by c into 1 minus c and this is that quantity. So, multiply dC on both. So, you get this, which was equal to some beta times dx. So, remember beta is equal to square root of a by kappa. Okay. Now, I am going to write this slightly modified. So, this is dC by c minus of minus dC by 1 minus c. is equal to beta dx, right, minus dc because the derivative of this is dc with a minus sign. So, I have introduced a minus sign. So, let us integrate dc by c is going to give me. So, what is that I have dc by c minus dc by 1 minus c equal to beta dx. So, logarithm of c minus logarithm of 1 minus c is equal to beta x. So, logarithm of c by 1 minus c equal to beta x. Okay. So, 1 minus c by c is basically exponential minus beta x. So, 1 by c minus 1 equal to exponential minus beta x, which implies 1 by c is equal to 1 plus exponential minus beta x, which implies c is equal to 1 by 1 plus e power minus beta x, which can further be simplified e by 1 by e beta x. So, that will go there. So, it will become e beta x by 1 plus e beta x. So, there are two ways of thinking about it. So, you multiply by e beta x on the top and on the bottom. So, you will get e beta x plus 1 because e beta x into e minus beta x will become 1. So, this is. So, we have found that the solution for the case that we are looking at is this. So, there is, so let me write this solution once more. So, c is equal to 1 by 1 plus e minus beta x, and this solution can also be written as e beta x by 1 plus e beta x, and this is also related to tan hyperbolic function. Okay. Why is this related to tan hyperbolic function? Let us think of tan h of x, which can be written as e power x minus e power minus x by e power x plus e power minus x. Now, divide by e power x both the top and bottom. So, you will get 1 minus e power minus 2 x by 1 plus e power minus 2 x. Okay. Now, let us take tan hyperbolic x plus 1 is equal to 1 plus 1 minus e power minus 2 x by 1 plus e power minus 2 x, that is equal to 1 plus e power minus 2 x plus 1 minus e power minus 2 x by 1 plus e power minus 2 x. This and this will go away. So, 1 plus tan hyperbolic x by 2 is nothing but 1 by 1 plus e power minus 2 x. So, we have this 1 by 1 plus e power minus beta x. So, it can also be written in terms of tan hyperbolic. So, if you do that translation, so what do we get? So, let us write it again. So, 1 by 1 plus e power minus 2 x is nothing but half into 1 plus tan hyperbolic x. The solution that we have, c is equal to 1 by 1 plus e power minus beta x, which can be written as half 1 plus tan hyperbolic, because if it is 2x it is x. So, if it is some x it is x by 2. So, we get beta x by 2 is the solution. Remember, tan hyperbolic x goes from minus 1 to plus 1 and you add 1 to it. So, it goes from 0 to 2, you divide by 2, it goes from 0 to 1. So, that is the solution that we were looking for. So, this automatically gives me the solution that we are looking for, right. So, what did we do to remind ourselves? We found out that for the given free energy functional, according to the thermodynamic definition of the interfacial energy. In our case, the free energy functional itself happens to be the interfacial energy functional. The system should choose that composition profile which minimizes the interfacial energy. So, it should obey the Euler Lagrange equation. So, we tried to calculate the Euler Lagrange equation, except that unlike the usual case, in this case we found out the Euler Lagrange equation for a very specific case of the integrand, the f not being an explicit function of x, because that makes life easier. So, we can then write a ordinary differential equation which can easily be solved, and the solution gives me this. Now, from this solution it is clear that beta, which is A by kappa, right. If kappa is 1, you will have some profile. If kappa becomes 4, then beta becomes half of what the initial one was, then the interface will become, because beta basically tells how sharp the tan hyperbolic function is. So, if it becomes half, then the interface profile is going to be much wider. Similarly, A also has the same relationship, except that it is in the numerator. So, if you make A instead of 1, for example 4, then the A has increased, which means the barrier has increased, but beta becomes twice. So, this number becomes larger, then the interface becomes sharper. So, this is physically agreeing with what we said last time. The interface that the system chooses. So, I have a composition profile where C equal to 0, I have another composition where C equal to 1. At both these extremes, we know that the dC by dx equal to 0, here also dC by dx equal to 0. So, if you look at the f expression, which has AC squared into 1 minus C whole squared plus k dC by dx whole squared, in the bulk both these terms are 0, in this bulk also both these terms are 0. Wherever, so if I say that I will have an interface which is sharp like this, up to this it will be constant, up to this it will be constant, this term will be 0, but at the interface dC by dx will blow up. So, that will give a huge contribution to the interfacial energy. On the other hand, if suppose the system takes an interface profile which looks like that, dC by dx will be very small. So, its contribution will be small, but AC squared 1 minus C squared has this. So, it will start getting points with composition all over here, and that will increase the energy. So, the system then chooses an interface which is trying to make sure that neither this quantity nor this quantity is too high. And in fact, that is what we derived in the earlier expression. Remember, the final expression that from which we tried to solve the equation was what? It said that kappa dC by dx whole squared should be equal to A C squared into 1 minus C whole squared, right. Interfacial energy minimum required, this is from where we started solving. In other words, the interface free energy has two terms, they should be equal, and this is what we found numerically. When we calculated the interfacial energy by integrating, we found that k dC by dx squared term and AC squared 1 minus C squared term, they were equal. Both were, for example, 0.16, and finally they led to 166 etc., and they led to an interfacial energy of 1/3. So, let us now do that part. I mean, let us calculate analytically the interfacial free energy and show that this is indeed 1/3. That is what I will do in the second part of this lecture. Thank you.